Hello, everybody. This will be the discussion for the adjacency matrix. The adjacency matrix actually, because let's actually run through this that fast so that you will really understand it better. So it is a square 2D array used to represent a graph where each cell indicates whether a pair of vertices is connected by an edge. For weighted graph, the matrix entries store the edge weights, providing a compact representation of all relationships between vertices. Actually, class, in our adjacency matrix, we have to define in our graph if they are adjacent to each other. We'll begin to see if they do have a relationship, and we'll begin to set also, we'll begin to identify how does that work. Because in our um calculate I mean illustrations that I'll begin to show you and how to run through that step by step, since that is really so simple. Because no worries in that, I'll begin to give you the illustrations in a while. Okay, so in this video I'll begin to just give you the discussions only. Now, how to build an adjacency matrix and for unweighted graph. To build an adjacency matrix for an unweighted graph, place a 1 in the matrix for any pair of vertices that are directly connected by an edge, and 0 where there is no edge. In undirected graph, the matrix is symmetric because edges do not have a direction. So that means to say, class, if there will be no value, there is no value in terms of that specific edge, you have to identify 1 as to represent that there is a relationship between that vertices. And then the 0, that signifies that no relationship, or they are not adjacent to each other. Actually, the this is really basic. And if also for the weighted graph, the adjacency matrix stores the actual weight of the edge instead of just as 1, so you will begin to indicate what will be the value. And for 0 or infinity is used to represent the absence of an edge between two vertices. So if there's no relationship, you just have to put 0 and the value itself if there will be a weights, for example. Okay, so just to be reminded that symmetric, actually, if you'll begin to um convert the specific row into column, it will still be as is for the undirected graph. Now, diagonal elements in adjacency matrix. What does that mean? Diagonal elements in the adjacency matrix represent the connection from a vertex to itself. So meaning it's actually a loop. However, it's always 0 since self loops are allowed in the graph. These diagonals entries store the loop's weight, while for graphs without self loop, these entries are typically set to 0. Commonly, class, there is actually no graph which is um not directed to their own vertex, since we're not able to create that much pertains to that kind of structures. However, if there will be, you just have to make sure that you were able to put adjacency that is considered adjacent to each other if they are the edge is connected to itself, that is that you must make sure that you'll begin to put a 1 still for that kind of example if there will be. Okay, so for the adjacency matrix class, for different graph type, the adjacency matrix for undirected graph is symmetric, meaning the matrix entry from ij must be equals to ja as well. What I mean is, if A and B is connected to each other, if they are adjacent, so of course B to A is also adjacent, because that is actually the representation of undirected graph. For directed graph, they are non-symmetric. That means to say, if A is equals to B, however, B is not equals to A. That's how you will begin to understand that one, okay? So a unweighted graph can be easily represented using a matrix where 1 indicates an edge between two vertices and 0 indicates the connection. For example, a graph with 3 vertices and 2 edges can be represented by a 3 by 3 matrix with ones in the corresponding places. So we'll begin to understand that in a while once we'll begin to illustrate that already, okay? I know that this is actually vague as right now, but of course it will be illustrated in a different video also. In a weighted graph class, the adjacency matrix is actually um will include the actual edge weights instead of ones. For instance, if there is an edge with a weight of 5 between vertex A and vertex B, the matrix will reflect this weight at both AB and BA if the graph is undirected. That's what I mean. That's what we mean. For the step 1, we have to consider that we need to identify the number of vertices to create the adjacency matrix. First, identify the number of vertices n in the graph. The matrix will be n by n. in this size, where each row and a column represents a one vertex. For example, if there are four vertices, the matrix will be 4 by 4. So that's how you'll begin to understand that one. For example, if there will be five vertices, you just have to anticipate that the matrix will become 5 by 5. Okay. Now, initialize the matrix, create a square matrix of size, and by n, initialize all elements of the matrix to 0. As initially, we assume no edges exist between the vertices. This matrix will eventually hold either 0 or 1 or edge weights for a weighted graph. So you have to normalize that in your program, it has been set to 0 accordingly. Now, mark edges between vertices for each pair of vertices UV that are connected by an edge. Set the matrix UV to 1. For the edge weight is an in a weighted graph, or the edge weight in weighted graph, you have to identify what will be the number. If the graph is undirected, also set VU to 1. If directed, the matrix is not symmetric. So what does that mean? If A is equals to B, if that is unweighted, you have to set that as to 1. But if the vertices is A and B, then there will be there will be a number. You have to identify the number, put the number already. But if B is equals to A, you have to identify 1 also for unweighted graph. But for for the directed graph, if B since there will be a cases that B is not also equals to A, so you have to be mindful in terms of that one. Okay. Now for weighted graph, instead of placing one in the matrix for each edge, insert the weight of the edge. For example, if there is an edge between vertex A and vertex B with a weight of 5, place 5 in the matrix and entry. A is to B and B is to A for an undirected graph. Then step 5, handle self loop. If self loops and edges connecting a vertex to itself exist in a graph, place the weight of the loop or 1 for the unweighted graph. If the diagonal elements of the matrix, if there are no self loops, the diagonal remains 0. So that's how it works. So when to use the adjacency matrix are most useful for dense graph where there are many adjacent edges relative to the number of vertices. They provide quick, constant time access to check if two vertices are connected, but they are less efficient for sparse graph due to the sparse required to store all possible connection. When we say dense graph class, there will be for 5 vertices, there will be many edges, for example. So the adjacency matrix is actually easy to implement right there. But for sparse graph, meaning for 5 vertices, there will be few edges only. Maybe there will be, it could be spanning tree for what will be going to happen in that case. Now, advantage of the adjacency matrix. One major advantage of this one, that they provide constant time access for checking whether there is an edge between two vertices. This means that checking if an edge exists between any two vertices can be done in constant time. When we say constant time, you can definitely check that there will be a relationship connecting to that link accordingly. So if you'll begin to check from A to B, checking in that adjacency, you can definitely anticipate that, wow, there is already a 1. So therefore, there will be an adjacent to into that kind of representation. So let me just drink for a while. The matrix format is simple and straightforward also to implement and making it easy to visualize graph relationship, especially for dense graph. So dense graph is absolutely the advantage of this one. For the disadvantages, one significant disadvantage is that adjacency matrices are space inefficient for sparse graph, since the matrix stores a value, for example, possible edge, including non-existing ones. Many entries are wasted with zeros, leading to wasted memory. So there will be a memory overhead pertains to that because we are allocating each of the adjacencies. Since you have to identify if there will be a relationship in terms of that, that's why it will be the disadvantages in terms of the adjacency matrix. Now, for sparse graph, the adjacency list might be a better representation as it only stores existing edges. So of course, that is the disadvantages though. So the application, dense graph, adjacency matrices are particularly useful for dense graph, where number of edges is close to the maximum possible number of edges. In such cases, the matrix is more efficient because it avoids the overhead of other representation like adjacency list. So in this cases here, class, in dense graph, since in our dense graph there will be many edges, so of course you will begin to solve those memory overhead, since in our linked list there will be memory overhead, extra spaces for each of the list. Then here, then each of the um adjacency, you have to identify if there will be relationship. So therefore you can definitely easily to identify, easily to implement, and of course, memory efficient for the dense graph alone. Now, can be used for the graph algorithm also. Many graph algorithms such as Freud-Warshall for finding shortest path rely on adjacency matrices for efficient edge lookup. However, in our discussion class, supposedly we'll begin to cover that. However, we will begin to discuss only the Dijkstra's algorithm as well as the um Bellman-Ford algorithm for our shortest path. Now, network representation used in networking, such as computer networks or social networks, where relationship between many entities need to be analyzed quickly, and the time complexity of adjacency matrices, the time complexity for checking in if an edge exists between two vertices is constant time. This is because the matrix allows direct access or to any entry in constant time. So, meaning to say, when you say 1 to 5, if there will be a direct relationship, so therefore they're adjacent to each other, and you can just check that directly into the adjacency matrix, and that is a constant, you can definitely know that there will be a relationship to each other. And time complexity, inserting or deleting an edge between, involves updating the matrix entry, which will takes linear time, wherein the n is the number of vertices. This is because the operation may require adjusting rows or column for all possible edges. Of course, since we are allocating each of the particular vertices also. Now, the space complexity here is quadratic time, where n is the number of vertices in the graph. This is because the matrix stores a value for each pair of vertices, resulting in a square matrix of n by n. So that's why it will be quadratic time. Even if a graph is a sparse, the space is required for an adjacency matrix remains proportional to quadratic time, which is inefficient for graph and fewer edges. So that's the representation in terms of the adjacency matrix class, and in the next video I'll begin to run through with the adjacency list, but I'll begin to make the video completely for the illustrations once I'll begin to finish with the discussions for the deliverables already. Okay, thank you so much, everybody. Bye for now.